Hello learners, welcome back to my channel Shraddha's Physics. In this video you will see the local electric field at an atom. So let us begin our topic, that is the local electric field at an atom. The local field, that is E local, it experienced by an atom or molecule or dipole. Usually it differs from the applied field. That is, this E localized field or the local electric field is not equal to the applied field. We will see what is the local electric field. So in a dielectric solid, the atoms or molecules it experiences not only the external applied electric field but also the electric field produced by the dipoles. So the resultant electric field acting on the atoms or the molecules of the dielectric substance is called the local field or an internal field. So in simple word I can say that the electric field produced by the dipoles and the resultant electric field acting on the atoms or the molecules of the dielectric substance is called the local field, or this is called the internal field. Now let us consider the two parallel plate capacitors. These are the two parallel plate capacitors, and a dielectric slab is inserted in between the two parallel plate capacitors. So this is your dielectric slab, this one is your dielectric slab, and these are your two parallel plate capacitors. Now let us consider a spherical cavity within this dielectric with the dimensions greater than the molecular dimension. Since from the previous classes we have already studied that since these are two charge plate capacitor, it contains suppose the positive charge, so that the surface charge density here is plus sigma, and this is your negative charge plate and it has the surface charge density minus sigma. Okay, this is your minus sigma. If we insert a dielectric slab in between these two parallel plate capacitor in this charge plate capacitor, you can say, now what will happen, because of this plus sigma and minus sigma, you can say the electric field will be in this direction. Now because of this dielectric, whether it may be polar molecules inside this dielectric or maybe the non-polar molecules, so the charge inside this dielectric, they will move in the opposite direction to that of the applied field. So now the negative charges, they will move just in the opposite direction to that of the field applied, and the positive charges, we can say that they will be move in the direction of the applied field. Now here, because of this charges separation, there will be a dipole moment. So here you can say that there will be an induced electric field will develop, and that is suppose, or the polarized electric field, that will be suppose EP. This is just because the surface charge density developed here is minus sigma p, and because of this positive charge, the surface charge density developed, that will be plus sigma p. Okay. So surface charge density means here because of the polarization, this is your surface charge density occurs. So this polarization charge density is nothing but the polarization charge per unit surface area. Okay. So let us consider a spherical cavity within the dielectric with the dimensions greater than the molecular dimension. Since the polarization occurs, we take the polarized charges per unit surface area of the cavity, that is sigma p, and the real charges per unit surface area of the capacitor plate as sigma. So these are your real charges for this plus sigma, and here is your minus sigma, and because of this dielectric, so the surface charge density will be plus sigma p and minus sigma p. Now the net field experienced by the molecule of the dielectric at the center C, that means at the center C, that is inside the spherical cavity, the center of the spherical cavity, if I want to calculate the electric field, so the net electric field will be equal to the net electric field, that is the E localized field, that will be equal to E1 plus E2 plus E3 plus E4. So what are these E1, E2, E3 and E4? So this total electric field experienced here at the center of the spherical cavity is known as the localized electric field. That is, it is nothing but the summation of all the electric fields experienced by the spherical cavity. So here let us see what are the E1, E2, E3 and E4. So E1 is the field between the two plates with no dielectric. So when there will be no dielectric, so in that case the electric field will be equal to sigma by epsilon naught, because sigma is because of the charge plate capacitor, the surface charge density, that will be sigma divided by epsilon naught. Epsilon naught is the permittivity of the free space. Now E2 is the field at the C due to the polarized charges on the plane surface of the dielectric. So now when you introduce a dielectric slab in between these two parallel plate capacitor, now the surface charge density, that is the polarized charge density developed, that is your sigma p. So the electric field will be equal to sigma p divided by epsilon naught. So this is the field at C due to the polarized charges on the plane surface of the dielectric. So the charges always develop on the surface of the dielectric. Okay, so on this part, okay, on the surface of the dielectric. Okay, and E3 equal to the field at C due to the polarized charges on the surface of the cavity to be calculated. So we will calculate this E3, that is this electric field at the point C, that is the center of the sphere, due to the polarized charges. So because of this polarized charges, we will calculate the electric field. Now E4 is the field at C due to the permanent dipole. So if you will consider the dipoles are permanent, means in case of the polar molecules already the charges are separated. So here there will be a permanent dipole moment. But here if I will consider for the non-polar case and the isotropic dielectric where there will be no permanent dipole moment, so we can consider this E4 to be 0. Okay. Or the electric field intensity at C due to the other atoms in the cavity, here we are assuming lattice has the cubic symmetry. So typically I can say that E4 value equal to 0 for the non-polar isotropic dielectric. Now if I will calculate the total electric field, that is E localized field, then E localized field equal to the sum over E1, E2, E3 and E4. Since here we are considering for the non-polar dielectric, so this E4 equal to 0. Now we have E1 plus E2 plus E3. This E1 is nothing but your sigma by epsilon naught when there will be no dielectric. When we introduce the dielectric, then this will be sigma p by epsilon naught. So here you can see, if I will consider this side, so this is your plus sigma, and in this part, because of this plus part, the negative charges will be get attracted towards this. So here the surface charge density will be minus sigma p. Similarly, if you will consider this minus charge plate capacitor, that is minus sigma, on the surface of the dielectric the charge developed will be plus sigma p. So here this will be sigma by epsilon naught minus sigma p divided by epsilon naught plus, because of this electric field, E3. Now I will write E3. This sigma by epsilon naught is for the charge plate capacitor when there will be no dielectric, we can say, and this sigma p by epsilon naught, this is for the when the dielectric is introduced between the charge plate capacitor. Now we can write this total you can see here the total electric field, that is the localized electric field, that is equal to sigma by epsilon naught minus sigma by epsilon naught plus E3. This sigma by epsilon naught minus sigma p by epsilon naught, this is your suppose E, and that is the resultant field between the plates, and this is plus E3. Now our main aim is to calculate the electric field, that is E3. Okay, one more thing, why we are giving this negative sign, because you know, let me show the diagram. Here you can see, because of this positive charge on the charge plate capacitor and the negative charge on the charge plate capacitor, you can see the electric field direction will be this, and this is your E1. Okay, now because of the polarization, the charge developed at this point, that is on the surface of the dielectric, the charge separation occurs in this way. Now the electric field that will try to induce, that will be E induced, or that is the EP, that is the polarized electric field. it is just in the opposite direction. That is, this E1 electric field, that is the applied electric field, and this EP, or let me write it as E2, this is your E2. This E2 is the electric field which will try to oppose this E1, or this is in the opposite direction to that of E1. So simply we will write this will be E1 minus E2. If I will write E1 minus E2, if I will write the magnitude, then this will be the total electric field will be E1 plus E2 plus E3 plus E4. But here, because of this direction, I will give a negative sign. So for that reason only, here we are putting the negative sign. Now let us calculate the value of E3. Let us consider a small elementary area ds on the surface of the cavity confined within an angle d theta at an angle theta with the direction of the field E. This is suppose the spherical cavity that is placed in between the charged plate capacitor. Okay. So here let us consider this is the diameter, that is A and B. This AB length is the diameter, and this is your, suppose the center is C. Now if I will consider this small area, that is the ds, and let me join this center to this point. This is your, it makes an angle d theta. So this angle is your d theta, and this surface area ds, it makes an angle theta with the diameter, suppose this AB. This is suppose the dielectric slab, and suppose suppose these are the two, this pink one, these are your parallel plate charge capacitor. So on this plate, these are your charge, that is your plus sigma, and here the charges developed, that is your minus sigma on the parallel plate capacitor. And the direction of the electric field, like this is your electric field because of the parallel plate capacitor, charged parallel plate capacitor. You have to just imagine this sphere is a three-dimensional figure. Now if I will consider the polarization will be in the direction of the electric field. So if this is the polarization, P, if I write this is the polarization P, then the polarization P will be parallel to the E, that is the electric field. So the polarization P will be parallel to the electric field. Now its component will be normal to the ds, will be Pn equal to, now let me show you, the normal component will be just like this. This is your, suppose the normal component Pn. Okay. Now this Pn will be equal to P cos theta. Now you can see here its component normal to the ds, it will be Pn equal to P cos theta. Since the polarization is also defined as the surface charges per unit area, so the charges on the ds will be, so we can write the charges on this surface area. So that is the, in this surface area the charges developed, that is suppose your q prime. So this q prime we can write, this will be equal to the polarization along the normal component into, along the normal direction, the polarization into the ds. Okay. So if we will take the dot product of this, then this will be nothing but this Pn will be equal to this Pn ds. Let me write Pn ds. So that will be simply Pn will be P cos theta into ds. This is P cos theta ds. Now we will calculate the electric field intensity at the point C due to this charge. So because of these charges, that is q prime, we will calculate the electric field intensity at the center C. So the electric field intensity at the point C due to this charge, that will be equal to 1 by 4 pi epsilon naught into q prime divided by r square. What is this r? So this r is nothing but the distance, this is your, the radius, that is r. Now if I substitute this q prime value, so this q prime is nothing but the P cos theta ds divided by, this will be r square. So the value of the electric field intensity at C due to this charge will be equal to 1 by 4 pi epsilon naught P cos theta ds divided by r square. and the direction is along the radius. So the direction will be along the radius, and r is the radius of the cavity, the spherical cavity. So the component of the intensity along the field E, that will be equal to 1 by 4 pi epsilon naught P cos theta ds by r square. So along the electric field, that will be your cos theta. That is for the parallel field, here the component will be cos theta, and for the perpendicular to the field E, that will be again the sin theta will be multiplied here. So the component of the intensity, this is your total intensity. Suppose I will write, this is your suppose E prime. So this E prime will be equal to 1 by 4 pi epsilon naught P cos theta ds by r square. This is the along the radius. But now if I will consider this electric field component, electric intensity component along the field direction, then simply for the component I will multiply cos theta, and for the perpendicular component I will multiply with the sin theta, that is your E prime sin theta, and this E prime is nothing but your 1 by 4 pi epsilon naught P cos theta ds divided by r square. Okay. Now we will calculate the value of ds. Okay. Now for this surface area ds, if I will consider a ring, suppose this is your 3-dimensional figure, I will just draw a straight line, but you have to just remember one thing, that is this is your sphere. So this will be in the ring shaped. So this part will be in the ring shape. This point is suppose L. This is your L point, and this point is your suppose M. Okay, this point is M, and this point is your suppose N, and this one is suppose, let me write this as suppose N. This point is suppose N, where it cuts the AB axis. This point is suppose N. Now if I can calculate this area, that is ds area, that is the ring area, you can see here, if you imagine this to be a ring, you have to imagine this d theta is very small. So this d theta component, if you will consider, so because of this convenient purpose, I have just drawn the larger in size. So because if you will consider here, the d theta is very very small. Now if you will draw this line, so now you can calculate the area of the ring. Okay. Now let me remove this. So basically I mean to say is that these two lines, they are very close to each other. That is the infinitesimal displacement. Now for this ring, if you consider like this ring, if you consider this ring in the 3-dimensional system here, so the area of the ring will be equal to, you can see here, if I will consider this to be the radius of the ring, now this angle is your theta. So what will be this side, that is mn side will be equal to, since the radius is r, so this part will be equal to, the perpendicular distance will be equal to r sin theta. Okay. Now if you will consider this here, the ring, if you will consider a ring having the radius r sin theta, then this will be 2 pi r, then this will be, so sorry, the circumference of the ring, first of all I will write, this will be 2 pi r sin theta. Okay. Now to calculate the ring area, I will consider, if I will consider this ds area, now this angle is d theta, this angle is d theta, and this side is your r, that is the radius is your r, so the arc will be equal to r d theta. So this will be your r d theta, this arc will be r d theta. Now if I will multiply this 2 pi r sin theta with the r d theta, you will get the ring area, that will be 2 pi r square sin theta d theta, that is equal to your ds. So now you can write the ring area will be equal to 2 pi r square sin theta d theta. Now if you substitute the value here, that is the component of the intensity along the field, that will be 1 by 4 pi epsilon naught P cos theta divided by r square, and in place of ds if I will substitute 2 pi r square sin theta d theta, then this will be equal to P cos theta ds into cos theta divided by 4 pi epsilon naught into r square. Okay. And again this will be equal to, in place of ds I will write 2 pi r square sin theta d theta. This is so simple. So now simply substituting the value, you will get this is cos theta into cos theta, that will be cos square theta, and this will be p divided by this 2 pi will get cancelled with this 4 pi and the remaining will be 2. Here is the epsilon and the sin theta d theta term remain as it is. Okay. So the intensity due to the normal components at the C will be 0 because they will cancel out. So you can see the normal component along this direction, they will be cancelled out. So the intensity at the C due to the whole spherical cavity, if we will calculate, E3 will be equal to the integration over 0 to pi this total value, that is p by 2 epsilon naught cos square theta into sin theta d theta. So now integrating within this limit 0 to pi, this p by 2 epsilon naught term is constant taken outside. This will be cos square theta, and we can write this sin theta d theta to be d of minus cos theta, because you know the derivative of cos theta, if we will take the derivative of cos theta, that will be equal to minus sin theta. This will be minus sin theta. So simply if I will write the d of minus cos theta, then this minus sign get cancelled. So this will be your sin theta. So now if I will write this to be d of minus cos theta, again I can integrate, that will be equal to p by 2 epsilon naught term remain as it is. This minus sign come here, and the cos square theta d theta, if we will consider that cos theta equal to x, if you just imagine cos theta equal to x, this is the integration over x square into d of minus x. So minus sign is taken outside. So this will be x square dx integration. This is simply s cube by 3. You can integrate in this way also, or you may consider that cos theta equal to x, and so on. You can solve in this way also. So this s cube by 3. So x is nothing but your cos. So this will be your cos cube theta by 3, and you have to integrate with from the 0 to pi. Then this will be equal to minus p by 2 into 3, that will be 6 epsilon naught whole into this cos pi value will be minus 1 whole cube. Again cos 0 is again your 1 minus 1 whole cube. Sorry, this is cos cube theta. So you have to put cos cube pi minus this is cos cube 0. So cos cube 0 is your minus 1, because cos 0 is your 1. So 1 cube is your 1, and cos cube pi, this is your minus 1 cube. So this will be minus 1, and here this will be minus 1. Since cos 0 is your 1, cos pi is your minus 1. Okay, cos 0 is your 1. So here you can see this will be minus p divided by 6 epsilon naught. This will be minus p divided by 6 epsilon naught whole into this will be minus 1 into minus 1, that will be minus 2. So this minus will get cancelled with this minus, because minus into minus plus. So this 2 with the 6, this will be p divided by 3 epsilon naught. Okay. So from this expression we have taken this total localized electric field equal to E1 plus E2 plus E3 plus E4, and here you can see simply we have considered this E1 plus E2 to be E, and this is your E3. Since E4 is your 0, so I can write the localized electric field, I can write this is equal to E plus E3. This E is nothing but E equal to sigma by epsilon naught, and this is your minus sigma pi by epsilon naught when the dielectric will be introduced. Now this E plus E3 value, in place of E3, now we can substitute P by 3 epsilon naught. This is your E3 value. So this will be equal to E plus P by 3 epsilon naught. So this equation, it represents the localized electric field in a dielectric for an atom or the cubic structure, and the internal field in a dielectric solid metal, and also this represents the Lorentz field for the elemental dielectrics. And also we know the displacement vector, that is electric displacement vector, you can see D equal to epsilon into E vector, or this is your epsilon naught E plus P vector. And also we can write this will be equal to, if I will write D equal to epsilon naught E plus P vector. Now from this expression I can write this will be D minus P that will be equal to epsilon naught into E vector. Or if I'll directly write, I can directly write from this expression, this D is nothing but your epsilon into E, and that is equal to epsilon naught E plus P. So from this expression, if I will calculate, that implies this will be epsilon. If I will take from this, electric field will be common, that is E will be taken common, this will be epsilon minus epsilon naught whole into E, that is equal to P. Or I can write this P will be equal to, sorry, the E will be equal to, I have to calculate the electric field. So E will be equal to, I will directly write this will be P divided by epsilon minus epsilon naught. Okay. So here you can see the value of E will be equal to P by epsilon minus epsilon naught. So this is the value of this. So in this place I will write this will be equal to P divided by epsilon minus epsilon naught, and this value will remain as it is, that will be P divided by 3 epsilon naught. Now we can see here, if I will just take common P by 3 epsilon naught here, then this will be equal to, let me solve it here. If I will take common P by 3 epsilon naught, this is P by 3 epsilon naught. So for the first term I will write 1 plus, this will be, P is taken already common, this will be 3 epsilon naught divided by epsilon minus epsilon naught. I can write like this, because you can see this will be P by 3 epsilon naught, when you get multiplied with 1 you will get this, and when you will get multiplied with this the second term, then this 3 epsilon naught get cancelled with the 3 epsilon naught, this will be P by epsilon minus epsilon naught. So this expression is correct. Now if I solve this, this will be equal to P by 3 epsilon naught into, taking epsilon minus epsilon naught to be the LCM, this will be epsilon minus epsilon naught plus 3 epsilon naught. Okay. So this will be 3 epsilon naught minus epsilon naught, this will be 2 epsilon naught. Again I can write this will be equal to P divided by 3 epsilon naught whole into epsilon plus 2 epsilon naught divided by epsilon minus epsilon naught. Now we can check the result. So this is nothing but P divided by 3 epsilon naught. You can see P divided by 3 epsilon naught whole into epsilon plus 2 epsilon naught divided by epsilon minus epsilon naught. So this expression is correct. So this is called the localized electric field. So that is the total electric field lies inside that spherical cavity will be equal to P by 3 epsilon naught whole into epsilon plus 2 epsilon naught divided by epsilon minus epsilon naught. So this is very important. So in this way you can calculate the localized electric field. So this is all for today. Thank you all.